Good evening, mga lagan. So we will continue discussing about the loadings. So from last video, we discussed a little bit about the funding load, and then so we already calculated the volume, which is um, so the total volume, right? So the total volume accumulated on the roof is 1,354.33 cubic feet. And then, so we already started this one, like how to calculate for the volume, but we will review on that one here. So going back to the roof plan or the floor plan. So like I said, so basically we have our distribution. We'll change the color. Uh, so so this will be our roof slope. Like so we have slope going this way, going that way, and then going that way, and then going that way. So assuming our um, roof drain is somewhere here in the middle. So that is our roof drain, that one. So to calculate for the volume, no, to calculate for the volume, so we will divide this into um, 5 segments. So we will divide it here. We'll draw a line, and then that one, that one there. So this entire area, this middle one here, within this hidden line boundary, we will call this area, wait, we will call it area 1, or say volume 1. So that is our volume 1. So this area between these two hidden lines. And then next would be this volume here. So we will call that volume 2. But there are 4 like of this area. So basically this volume 1, and then this one here 2, and then 3, and then 4. So that comprises the total volume of the water that will be accumulated in the in on the roof. No? So to calculate for the, so we already talked about the change in elevation. So this one we will draw a cross section. So this is your wall, and then we will just exaggerate the slope. That one. No. So we'll just exaggerate the slope. So this one here, so we will draw a line between the end to end of the roof. So this is our volume 1. And then we already talked about the change in elevation here between the highest point of the roof and the lowest one. We have, uh, so this is 6 inches, right? So that is 6 inches, the change in, or the change in elevation. So the highest point is 6 inches higher than the roof drain elevation. Now, our truss, so the truss, the total deflection, or the allowable deflection for our roof truss is L over, um, we can have L over 240 for the snow load, and then L over 180 for the total load. So this is total. Now, for to get the maximum or possible maximum depth at the very center of the roof is you will have 6 inches, the change in elevation, and then you will add the possible total or maximum deflection, which is equal to the allowable deflection. That's the worst case. I mean, if it's more than that, I mean, it's already considered as failed, like the structure. So when the roof truss manufacturer design the truss, it is intended for, basically it is designed to meet the maximum deflection of L over 180 for the total load, and then 1 over, or yeah, L over 240 for the snow load. So we have we already have the roof dead load, which is, how much was our dead load from last time? Was that 30? Yeah, 30. So our dead load is 30 PSF. So our dead load is 30 PSF. What's going on with this? And then our roof snow load is 38.9. Now, by the way, if you notice, we did not consider any roof live load, which is, for example, if you are using the IBC, the International Building Code in the US, there is in the load combination, you have the roof snow load. Even in the Philippines, we have the um, roof snow load, which is 20 PSF. Correction, this is not
But
snow load. This
in
is,
Canada,
I'm referring, the 20 PSF
although
I'm
it is
referring is
mentioned
the
in the
roof live load,
it
not
is
the snow
mentioned
load.
in the building code, but I don't know if there is a location here in Canada where the snow load is less than 20. So if ever there is a, say, town or city which is less than 20 PSF, then you have to use the minimum, which is 20 PSF for the roof live load. Now we'll see. We'll try um the Vancouver area. We'll just see if for example, Victoria, that is already in the Pacific. So we will see if the snow load is less than 20. So we'll go here, Jabacos, and then roof snow load, and then Victoria is in British Columbia. Victoria, Vancouver region, Victoria. So we have three: Victoria region, Victoria. I don't know what's Gonzales Heights and Mount Tolmi. So we'll just check this one, Victoria. See, even in Victoria, it is in the coastal
it's a coastal city. That's the capital of British Columbia. So that is already 22.6, which is higher than the roof snow load of 20 PSF or 1 kilopascal. So again, 20 PSF is the
I think
roof
the
live
reason
load.
why it is not mentioned in
The load combination, um, if we look at the load combination, Alberta Building Code, and then structural is 393, page 393. If you look at the load combination here, see? So in the load combination, we have the principal loads and the companion loads. So 1.4 dead load, that's a principal load. And then the second case would be 1.25 dead load or zero point 0.9 dead load. And then 1.5 live load. And then on the companion load is either 1.0 is no load or zero point 0.4 wind load. So there is no roof live load because I don't think there is any town or city or municipality here in Canada where the roof snow load is less than 20 PSF. So unlike in the US, let's check IBC. See, unlike here, I don't know if you can see this. So the load factor, like in Canada, in National Building Code of Canada, the load combination, the load factor for dead load is 1.25, and then live load is 1.5. In IBC in the US, the load combination for dead load, the load factor for dead load is 1.2, and then 1.6 for the live load. And then in the Philippines, dead load is 1.4, and then live load is 1.7. So when you calculate for your load, of course, you have to check. I mean, it has to be based on the load combination from the building code where you are designing your structure. So So if you notice here, 1.2 did load, and then F, I think this is fluid. Is it fluid? And then 1.6 live load plus hydrostatic, and then zero point 0.5 live load, roof live load, this L sub R. So that is the roof live load, or the snow load, or the rain load, whichever governs. So in Texas, for example, the snow load is only 5 PSF. So in the US, there are times that the roof snow load governs. But in the US, say Montana or um, probably Colorado or Idaho, it is interior and then almost basically next to the border with Canada. So I assume the snow load there is really huge compared to, or I would say bigger than the specified roof snow load, like minimum, which is 20 PSF. So where's it? So where were we? So 35 PSF for our snow load for the SLS. So going back to the um, possible like maximum deflection. So L over 180, we will use L over 180. And then this is, so assuming our roof would span um, 60 feet, it could, yeah, it could probably span 60 feet. That's fine. I mean, there are times that the if your building height is there's a restriction to your building height, and then you need the underside of truss to be at that elevation, then you are restricted with the height of your trusses. Then what you can do, instead of full span 60 feet, what you can do is you can have um, let's try another page. So what you can do is you will have a girder truss here. So you will have a girder truss. Oh, wait. So if you are restricted with the maximum height you can have for the truss, to make it shallower, you can divide the span by half, and then you introduce a girder truss in the middle, and then this will be your roof trusses. But this girder truss, that's too long, like 80 feet. We might need to break that also into half or cut that into half, and then provide a another column here. So those are like another option for your roof framing. But if you want a clear floor area, you don't want any column, then your only option is basically span the whole truss all the way, like end to end. No girder truss in the middle. So for example, the client or the owner doesn't want any interior column, then you have to span the whole depth of the building, which is 60 feet. So 60 feet. So at L over 180, 60 times 12 over 180 is equal to 4. 4, no? Yeah, 4 inches. So we already have like the change in elevation from the perimeter, the highest level of the roof, and the lowest level is 6 inches. Therefore, our total depth is equal to 10 inches. So this is our maximum or deepest, like possible deepest water um, height on the roof. So going back, or let's have another page. So from here, right, this is our roof. So the truss is already deflected by 6 inches or 4 inches, and then you have also the change in elevation of um, 6 inches. Therefore, this height, this one, this is 10 inches, right? So that's 10 inches. So therefore, our volume for this one here, this is the total width is 60 feet. So therefore, the volume is equal to 1/2 of 60 times 10 over 12, and then will it fit? No. Then times the width for example, let's go back to our floor plan, or no, this one here. So if this is 60 feet, this one is 30 in the middle, and then this is at 45 degrees. So that means if this is 30, this is also, this is also, I mean, if this is 30, this is also 30. So if this is 30, this is 30, and then the total is 80. Therefore, this one here in the middle is 20 feet. So from here, this is times 20 feet. So that is the volume. This is volume 1, uh, right? So volume 1, this one, volume 1. This one here, this highlighted with yellow. So this is our volume 1, this one in the middle. So volume 1 is uh, 60 times 20. So this is 500. Wait. So this is equal to 500 cubic feet. So in our, so therefore from our, so our slope, this one here, so this area, this is 500, or the volume in this section is 500 cubic feet. Now we will calculate for this volume here, and then we will multiply it by 4 to, and then add to the volume 1, which is 500, and we will get the maximum or the total volume. So this area, so if we draw that in 3D, we will do that in 3D. So it will look like this one. So this is 10 inches. This one from here to here, right? That's the total depth at the lowest point. And then the height here is 0, 0, 0. So to get the volume is equal to the area, this one, the area times the average height. So this is the same calculation if you, for example, for like in surveying, cut and fill, and then you will measure or calculate the volume of your cut, or volume of your fill, where you have four corners, and then just get the average, and then multiply by the area, that is your volume. So for the height, so volume is equal to area times height. Therefore, and then height is equal to 0 plus 0 plus 0 plus 10, and then over 4. So the average height is 2.5 inches. So that's the average height for this entire section. So therefore, volume is equal to the area of this one here, which is 30 times 30. So this is 30, half of 60, and then this is also, because this is 45, so this is also 30. So 30 times 30 times the height, which is 2.5 over 12. So you will have the volume of 30 times 30. 187 0.5 cubic feet. So therefore, our total volume total is equal to V1 plus V2 times 4. And then this is 500 plus 187.5 times 4. And then the volume would be times 4 plus 500. This is 1 to 50, right? So that is 1 to 50 cubic feet. And then what's our volume of water? Our volume of water is 1354.33. 1354.33. So it means the volume of water that can be accumulated based on the 1 day 1 in 50 year occurrence precipitation is 1,354.33 cubic feet. But your roof can only accommodate 1,250 cubic feet. Now this is the volume up to the uh, top or the highest point of your roof. We haven't considered the surface tension yet, which is 30 millimeter. So going back to your roof section, so going back to this section, this volume is 1 to 80 cubic feet. And then our scupper is flush with the bottom of the scupper is flush with the top of the roof. But like I said in the code, you have to consider extra 30 millimeter height for the surface tension before the water starts to flow out of the scupper. So it means you still have extra you still have extra 30 millimeter water that you should consider. So 30 millimeter, how much is that in inches? 30 divided by 25.4 and then in feet. That is point 30 millimeter is equal to 0.099 feet. That one. So the volume, this one of the portion like the 30 millimeter. So the volume is point zero 0.099 times 80 times 60. That's the area of your roof. So 0.099 times 80 times 60, that is 400. So this is 472.44. Uh, going on here. So volume is 472.44 cubic feet. Now you will add this one to the 1,280 cubic feet. So the total volume of, like, possible volume, like maximum volume that can accumulate on top of the roof before it starts flowing out of this copper. The total volume would be the this volume here. Don't be confused. This total volume, that is only from the lowest point of the roof to the highest point of the roof. Then you add that with the volume, like extra height, which is 30 millimeter for the surface tension. So the volume total is one was that 1 to 50? Yeah, 1 to 50 plus 472.44. Therefore, the total volume is plus 1 to 50 is 1722.44. Now, this is now higher than the total volume from the precipitation. So, therefore, at maximum precipitation, like 1 in 50 year for like one day occurrence, it will not fully um, occupy, or, well, it will occupy the roof, but not the total, the maximum height um, allowed, which is 10 inches plus 30 millimeter, right? So what we will do now is, instead of using this total volume, we will now calculate what's the difference between the two. So 1722.44. So the net, I would say net volume, the net volume above the highest roof is only 1722.44 minus 1354. Let's check. 1722.44, and then minus 1354.33. So therefore, that is 1354.33. This is 368.11 cubic feet. Now, to determine the height for this one, you will have to, the net height would be 368.11 divided by 80 times 60. So that's the area of the roof divided by 80 times 60. So this is 0.076 feet, or equal to times 12. This is 0.92 inches. So therefore, going back to our roof section, so including the extra um point, how much? 0.92 inches. Therefore, our maximum height for the for so this is already above the top the highest elevation of the roof. So therefore, this is the total height is 10.92 inches. So 10.92, that is 6 for the difference in elevation, plus 4 inches for the possible, like, maximum deflection of your truss, and then plus the extra um, height, which is below the 30 millimeter like surface tension height, which is 0.92. So that's why we have the height of 10.92. Now, we will calculate how much is the water pressure at the highest level. So the water pressure is, the pressure is gamma times height. So unit weight of water in imperial is 60, 62.4. This is pounds per cubic feet. Then times the height, which is 10.92 inches. 10.92 over 12. Therefore, our water pressure at the deepest level, at the center of your building, so plus 10 divided by 12 times 62.4. So therefore, the water pressure is 56.78. And then your water pressure at the highest level is 62.4. At the highest level, 62.4 times the height, which is 0.92. So 0.92 inches divided by 12 times 62.4. So your load here, or your water pressure at the highest level is 4.78 psf. So, oh, um, so this one, it's not the, it is covered by my camera, but so this is just the height, which is 10.92. This one, 10.92 over 12, and then that gives us the pressure at the bottom here is 56.78. This one, 56.78 kilopas or PSF, and then at the highest elevation where our water is only 0.92 inches, our pressure is 4.72. So for the funding, um, so we'll have another page. So on our roof structure, for the funding, the red is funding. So this is 4.78, and then this is 56.78. And then for our snow load is no, or let's uh, let's use this one. So for our snow is um what we call this one, 38. So this is 38.8 all throughout, uniform. So therefore, at the very bottom, the funding load governs at the lowest point. Now, if ever the funding load, this one, 56.78, or whatever is this funding value, if it happens that it is lower or smaller than the snow load, then just forget the funding. It will never govern because, for example, if the funding comes out as, say, 32 PSF. So for example, if the funding load at the very lowest portion of your roof is only 32, then you just disregard the funding because our snow load is already 38.8. So it will not govern no matter what. But in this case, our snow load or our snow load is 38.8, but our funding load, although this is tapered, right? Tapered highest at the very bottom.
which is 56.78, then you have to do in the load combinations when you design your say roof truss, you have to indicate that in the roof framing plan, you have to indicate how much is the snow load and then how much would be the funding load. So when the truss manufacturer sees that there is a funding load that needs to be considered, then they will consider funding load in the calculation. And then on your case, when you design for example for the studs or for the beam, then you have to account for the funding load also. And then another calculation, another load combination for the so for example, um, going back to the load combination from NBCC or Alberta Building Code. So we have here 1.25 plus 1.5 live load and then 1.0 snow load. So we'll use that combination. Our companion load is 1.0. So our load combination 1.25 D plus 1.5 L and then plus 1.0 S. That's your case 1. Now, since this is roof and there is no live load, then disregard that portion, right? If ever, for example, this is a rooftop where there is for example, this is a restaurant, and then the owner will decide, okay, on the roof we will have a small like a patio on the roof, um, where you can gather as well, like assembly. Then you will consider this whichever governs, either 1.5 is no load or 1.5 live load, which is live load for a like an assembly area, which is 100 versus this no load. So in this case, if this is a roof, then the 1.5 live plus 1.0 snow governs. Or no, you will only check whichever this one is bigger, either the live load or the snow load. Because if this is a patio, right, during winter, there's nobody that will occupy there. So that's why you will only select whichever produce the maximum value here. It's either snow during winter or um, live load during summer. Because the patio is only occupied during summer. I don't know if there's any restaurant here where even during winter there is people on the roof. I don't think so. So this is load case 1, right? But for load case 2, for load case 2, oh no. So 1.25 dead load and then 1.5 live load and then 1 point snow load. So like I said, um, if this in our case where there is no possible like live load on the roof, just disregard the live load case. And then on the second case, case 2 would be 1.25. So 1.25 did load, then plus 1.5 is no. Oh, 1.5 is no. Plus this time it is the live load which is having a load factor of 1. So like I said, there is no live load. Therefore, the governing load combination is this one. 1.25 did load and then 1.5 is no load. But since our funding load is higher than this no load, then we have to add one more combination, say 2A. Our 2A is 1.25 bid load plus 1.5 funding load. So that is your second load case when you design your roof structure.
we included this funding load just because our load at the very bottom is higher than the snow load. So like I said, if so like I said, if the funding load is say 32, which is lower than the snow load, then just completely disregard the funding load. But since our funding load at the very bottom is higher than the snow load, then we will have two load combinations for the roof. So one for the live load, did load plus no load, and then another one for the did load plus funding load. So we'll just take note of that one when we start designing our structure. We will make sure that we have two, like when we size the truss, or not really size the truss, but even if like to get the reaction from the truss itself, even if it is designed, even though it is designed by other a third party like a truss manufacturer, I still calculate for the just a representation of the truss so that I will know how much is the reaction at each end, and then apply that load to your studs or to your roof beam. So I think we are done with the funding load. Then Jesus, we're already 48 minutes. Just that's all. Like I said, our time, like we've been discussing this funding, like the second half of the funding load for 48 minutes already. So I guess we will do the wind loading and seismic loading because that would take time as well. Even the wind load, I would say wind load, we will um, allot a maybe one we will have one episode just for the wind load, and then probably one episode for the seismic load, because we have to look at um the code provisions for the wind load, like what to assume for your structure, if you can use a static equivalent static load versus dynamic analysis, and then yeah, that would take time. So for this is already part 2A. No, part 2B. This will be part 2B. Part 2A is dead load, live load, snow drift. That's part 2A for the loadings. And then part 2B for the loadings is second half of the funding. And then probably part 2C is dedicated for wind load. And then part 2D would be dedicated just for the seismic load. So please subscribe if you haven't subscribed yet. And then we'll see you on the next video. Bye mga lagan.